Hello students, welcome to lecture number 2 of force, moment of force and the equilibrium. So in this video, I'm going to teach you the remaining part of this chapter. In the last video, that is in lecture number 1, we studied about what are the types of motions, that is linear motion and rotational motion. What is the moment of force, which is torque. And now we are going to see 3 points in this video. First is the couple, second is the moment of couple, and third is equilibrium. If you have not yet seen the first video, the description link is given. The video link is given in the description. You can first watch that video and then come to this part. Also, I want to tell you that you can download the app. The link is given where you can get the videos, the test series, and different courses for you. Okay, so let us start without wasting any time. So, first thing, couple. Before we start, look at these diagrams. Are you able to see the diagrams properly, clearly? See. In all the three diagrams, you can see a few similarities. This is the, the car, what we say, the handle, the steering, right? So you can see when we rotate the steering, we apply two forces. One, let us say in downward direction, and the one in upward direction. So one towards you, one towards me, like this. We rotate the steering like this. Okay. When we pedal the cycle, you can see one foot is applying the force forward while the other is applying the force backwards. So there are two forces in opposite direction. So when we have this condition, two forces which are equal in magnitude. Note down, two forces equal in magnitude and opposite in direction. Then it constitutes a couple. It is nothing but a torque, the moment of force, the turning effect of force. But the only thing is we have two forces, equal magnitude and opposite direction. So let us see what your textbook says. So couple, a single force applied on a pivoted body alone does not cause the rotation of the body. So if you have a single force, then it do not cause rotation of the body. Actually, the rotation is always produced by a pair of forces. A single force cannot produce pure rotation. You can try. Take anything, a pen, and apply a force. The body will move in a forward direction. So it always requires two forces, a pair of force to produce a pure rotation. It will rotate at its own point. Okay. In the above example, the rotation is due to the force externally applied and the force of reaction produced at the pivoted point. So, I have one question from a student who says, sir, when I pivot a body, I fix a body. Or example of a door. So, I have a door and what I do is, I apply the force only at one point and still it rotates. So you are telling us the wrong concept that two forces are required. No, it is not the case. Here there is only one force, but the other force is applied by the reaction of this hinge. There are the hinges here, and that hinge is giving the force in the opposite direction, and because of which there is a rotation effect. So when I apply the force here, there is a force by this hinge in the opposite direction. So there are these two pairs. A pair is required. Two forces are required. So what the text is saying is the moment of force of reaction about the pivot is 0 because its distance from the axis of rotation is 0. So the force of reaction at the fixed point is not shown. Such a pair of forces is called as a couple. Thus, two equal and opposite parallel forces not acting along the same line forms a couple. It means that if you have two forces, two equal and opposite forces, which do not act along the same line, it constitutes a couple. You can see if there is a tab, one force is acting here while the other force is acting here. They are not along the same line. It constitutes a couple. Even a key, when we rotate the key, I have a key here. You can see my fingers. They are not acting on the same line. One force is acting this towards you and this is away from you, right? Like this. See, you can try. Look properly. Okay. And even the steering wheel, one force is in this direction, other is in this direction. When we open the, the cap of any bottle, these fingers apply the force in one direction while the thumb applies the force in one direction. Try to open the cap of a bottle with one finger. It is not possible. Even if it is possible, actually there is a reaction force. So when we use two fingers, see, it is easy to open. Okay. So you got the concept that the couple is nothing but when two forces acts on a body not along the same line, it produces the effect of rotation, and that is called as the couple. Now let us calculate the physical quantity related to the couple, and that is called as the moment of couple. The moment of couple. It is similar to the moment of force. Moment of force. Moment of force. You remember we studied this in the lecture 1. This is studied in the lecture 1. And it was like, if this is the body and you are applying a force here, then you need a perpendicular distance. This is the perpendicular distance and this is the force. So the moment of force is perpendicular distance into force. This is what we have studied in lecture 1. Now what is moment of couple? Because now we don't have one force, we have two forces. So let us say this is a rod and I am applying two forces, one here and other here. Are the forces acting along the same line? No, the forces are not acting along the same line, right? Because the line of this force is this, you can see. While this force is acting along this line, the line is not same. Because you might think, sir, see na, this is the same line. No, along the same line. Okay. So what is the moment of couple? So it is simple. The magnitude of any one force, because they have same magnitude, the moment of couple is the magnitude of force, any one force, into perpendicular distance between the force. Perpendicular distance. So let us say this is the perpendicular distance. So magnitude of this force into the perpendicular distance. The product of these two is called as the moment of couple. So simply it is the moment of couple is r perpendicular into magnitude of any one force. A thought question for you. Can I get the same formula by individually calculating the moment of this force and moment of this force? If I apply this concept, a moment of force, in the moment of couple, can I get the same formula? Think. I know you can do this. And the answer is yes. You can do this. See, force, let us say the point of rotation is this. Force into this distance, r by 2, half of the distance, in this direction, right? I have taught you this. This is anti-clockwise. Anti-clockwise moment is there. Even this force is also producing an anti-clockwise effect. So force into this distance, r by 2. So the moment of this force is F into r by 2. and the moment of this force is F into R by 2. Simply add them. R by 2 plus R by 2 becomes R, and you get this formula, moment of couple. Pause the video, take down the notes. Do it yourself. So let us see what your text is saying. The moment of couple. See? Uh, you can see there is a bar AB. This is bar AB. The distance is D. They have taken the distance D. Then, which is C. Two equal and opposite forces, each of magnitude F, are applied perpendicular to the distance between the two forces AB. The perpendicular distance is AB, which is called as the couple arm. This is called as the couple arm. Okay. So what we can do is, then two forces cannot produce the translational motion as their resultant sum in any direction is 0. This is a line we have to discuss. The two forces cannot produce the translation motion. The two forces cannot produce the translation motion. The reason, one force is in this direction while the other force is in that direction. So the body is not going to move either in this direction or in that direction. So the net motion of the body, or the center of mass of the body, center, is not going to move. See, if I apply a force in this direction, another force in this direction, the body will rotate at the same point, about one point. The entire body is not going to move from its position. The center is going to remain stationary. But each force has a turning effect on the bar in the same direction. Even though there is no translation motion, but there is a turning effect. See, there is a turning effect. There is no translational effect, but there is a turning effect. Thus, two forces together forms a couple which rotates the bar about point O. Yes, there is a motion about point O, right, in anti-clockwise direction. See, this is the anti-clockwise direction. Even this force is also producing the anti-clockwise motion. Okay, so moment of force F at point A. Moment of force at point A is F into this distance AO. AO. See, moment of force F at point B. This force is also producing some moment. This is F into OB. F into OB. And if we add them, F is common. OA plus OB. See, OA plus OB. OA plus OB. It becomes total distance D. So it is F into D. And this is the moment of couple in anti-clockwise direction. So moment of couple is, the formula is either force, any one of them, into perpendicular distance between the two forces. So to calculate the moment of the force, moment of the couple, we want magnitude of the force, either one, and the perpendicular distance between them. Simply, I am also going to solve few numericals for you, but first let us complete the theory part. Till this point, are you with me? Just post your name, class, school, city in the comment section so that I can know who is watching the lectures very seriously and who is the serious one. And I am sure everybody is getting the benefit out of these lectures. Okay. Next, so we have done with what is a couple and what is a moment of couple. Now let us come to the point of what is equilibrium. So what is equilibrium? So there are two types of equilibrium. One is the linear equilibrium and other is the rotational equilibrium. So let us study them one by one. So my question to all of you is, tell me what will happen if I apply a force F on this block and the block is placed on a frictionless surface. What will happen? There is no friction, there is a block, and I apply a force. And you will simply say, sir, the block will be set into motion. Because there is force, there will be acceleration. And because there is acceleration, there will be the change in the velocity. So its velocity will change because of the force. But now, what if I say I apply two forces which are in this way? One is F and one is 2F. What will happen? And you will say, sir, this force is in greater magnitude, so the body will move towards the left. And obviously that is the correct answer. Third case, what will happen if I apply two equal and opposite forces? And you will say, sir, the body will or may remain in the state it was. If it was in the state of rest, it will remain in the state of rest. Newton's first law. Or if it is in the state of motion, it will remain in the state of motion, the law of inertia. So this is called as the linear equilibrium. The linear equilibrium. So what is linear equilibrium? The equilibrium in which the resultant of all the forces is zero. This is the symbol of summation. Summation means addition. If we add all the forces acting on the body, and if the resultant is zero, then you can say that the force is zero and the body will remain in linear equilibrium. Linear equilibrium means it will, if it is in rest, it will remain in rest, and if it is in motion, it will remain in that state only. So let us say I have a block and it is applied with the force F. Let us take the scenario. The velocity will increase, it will go on increasing, and the velocity will increase. And let us say at some point the velocity is 5 meters per second. At that specific instant, when the velocity is 5, at the same instant I start to apply one more force. I start to apply one more force in the opposite direction. What do you think? Will the body come to the state of rest, or will the body will continue its motion? Some might think that, sir, this force will retard the body, stop the body. And some might say that, sir, it will continue. And the correct answer, boys and girls, is it will continue its initial state. As it was in motion, and this force will cancel out this force, there is nobody to decrease this or increase this velocity. So it will remain as it is. If it was in motion, it will go in motion, and if it is in rest, it will remain in rest. How is it? So let us say if I have a block and it is in rest, and at the same time I apply two forces, one in this direction, one in this direction. You and your brother, if you don't have a brother, then your friend, at the same time you apply the force, zup, what will happen? If it is in rest, it will remain in the state of rest. That's it. And this is the linear equilibrium. Got it completely? Now let us come to rotational equilibrium. Now let us say I have a rod and I have pivoted it here. Okay. And I start to apply force in this direction. And let us say it is free to rotate. the rod is free to rotate like this. Let us say this is the rod and it is free to rotate. I apply the force here. Okay, and it is free to rotate. Obviously it will rotate. It will not stop. It will rotate. So what if at the instant I apply the force, I apply another force to produce an opposite moment? Let us do this thing once again. I know it was a bouncer for you. What will happen in this case? There is a force, there is a perpendicular distance, so there is a moment of force. Moment in anti-clockwise direction. Anti-clockwise direction. But what I said after that is, what if I apply the force at the same instant this force was applied but in this direction, and the force is same, the distance is same, but now this force is producing an effect of clockwise moment. It is producing a clockwise moment. So anybody can assume and anybody can conclude that, sir, the rod will neither rotate in this direction and nor in this direction, so it will not be set in the rotational motion. So we can say that it is in rotational equilibrium, and this concept is called as rotational equilibrium. A rotational equilibrium. So let us say there is a seesaw and you are sitting, your friend is sitting here. Okay, he is holding this handle and he is of 50 kg. Okay, and this side you place a 50 kg block. What will happen? Come on, tell me. Will this person and this block come to equilibrium? What do you think? Very interesting question. And the answer is no. It will remain where it is. It will remain where it is. The reason is this force and this distance is equals to this force and this distance. So there is no torque. Remember. So, but you will say, so but when we play seesaw and if there are two masses and they come to equilibrium, no. See, when let us say this person is sitting, it applies the extra force. It's like it jumps and he applies a impulse, jerk, and because of that it comes away. But if we gently place this mass without any extra force, in our real life what we do is we jump. Whoa. So because of that, it gets extra impulse, extra angular momentum, extra moment of force, and because of which, they come to the same level. There is a force, and plus there is resistance. There is the person up also, with his foot, he applied the force. This person, this with the help of his feet, he's applying some force. But the situation I'm talking about is 50 kg sitting gently with his legs above the ground, 50 kg block placed very gently, no friction, nothing, no other force. It will not come there. But if it is 51, yes, the moment from this side will be greater to moment from this side, and hence this will win the war. Do you want to see one animation? So let me show you one animation. Okay, ready? So I have this FET animation simulations. So first let me drop the mass. So I will not show you the ruler. There are some markings which you can see: 1, half, 1, 1.5, 2, 2.5, 3, 3.5, 4. Same way on this side also. Now there is no mass, so the rod is in equilibrium. So I place this 5 kg, let us say at the end. So at a marking of 1, 2, 3, 4. So the moment is 5 into 4, something 20 units. 5 kg weight into 4 units of distance. So roughly it is 20 units. Let us not go into actual mathematics, just talk it quantitatively. And if I place this 10 kg, if I place this 10 kg on this side, before I place, guess your answer. What will happen? This is 5 kg and this is 10 kg. Because of this 10 kg, will the plank get horizontal or will it turn to this side? So you have to ask me a question, sir, where are you placing the 10 kg weight? So let me place the 10 kg weight here. Nothing happened. Even if it is 10 kg, nothing happened because the moment of this 10 kg weight is 10 into half, that is 5. So if I place it at position of 1 marking, so 10 into 1 is, that is 10. 10 into 2, that is 20. Yes. Now see, 10 into 2, 20 units of moment. 5 into 4, that is 20 units of moment. So the plank got, it came to equilibrium. And this is called as rotational equilibrium. This is called as rotational equilibrium. So if I slightly shift this mark here, now you can see that the moment of 10 kg weight is more than the moment of 5 kg, and hence it, it got tilted on that side. Simple concept. You can also, try this. So I have this, let us say 15 kg. 15 kg is, let us say at 1, 2, 3 unit distance, and I have another 20 kg at 1, 2. So before I remove this support, guess your answer. What is going to happen? Is it going to move towards left or is it going to move towards right, and why? Let me leave this question for you as a homework. Oh, so let us do, and I will give you next question for homework. See what happened. The 15 kg weight dominated this 20 kg weight. Why? Because 15 into 1, 2, 3, 15 3 is a 45. 20 into 1, 2, 22 is a 40. So 45 is greater than 40. So the moment from that side is more about this point. So one more question. So it is 10 into, yes, and this 5 into this and 10 into this. So you can just zoom and you can, are you able to see? Let me check. Yes, there is no problem, no problem. So this is a homework for you. Just comment your answer in the homework in the comment section. Okay. So let's come back. So now you have understood what is linear equilibrium and what is rotational equilibrium. Now my questions to you are, first question, is it necessary that when the body is in linear equilibrium, it has to be in rotational equilibrium? My question is, if there is linear equilibrium, that is the summation of all the forces is 0. Is it necessary that the body must be in rotational equilibrium? So the answer is not necessary. The answer is may or may not. If the body is in linear equilibrium, it is it simply means that there are two forces which are equal and opposite, but these two forces still can produce the motion. And this is what we have studied in the moment of force, moment of couple. Couple, two equal and opposite forces still produces a rotational effect. Getting it? See, if these two forces are acting along the same line, yes, only then you can say that this force and this force produces no couple at all, because they are acting on a same line. So the answer is may or may not. Both the situations are possible. Write this, pause the video, think, read, and then only you can understand physics. Physics is not at all difficult. It is only how deeply you think. It is how properly, how thoroughly you read the concepts. It is how you spend time to think, right? So when there is linear equilibrium, it is not necessary the body must be in rotational equilibrium, and vice versa. If the body is in rotational equilibrium, it is not necessary the body must be in linear equilibrium. So to get the ultimate equilibrium, total equilibrium that we say, the total equilibrium condition, to get the total equilibrium, we must have the linear equilibrium as well as rotational equilibrium, and then we can say the body is in complete equilibrium. If the body is only in linear equilibrium and not in rotational, it is not in total equilibrium, absolute equilibrium. It is partial equilibrium, linear equilibrium, translational equilibrium, or rotational equilibrium. So for linear equilibrium, the summation of force must be 0, and for rotational equilibrium, the net moment, the net moment of forces must be 0. That is addition, that is summation of moment of forces must be 0. And this is the condition for rotation. And if both the conditions are there, then only the body is in complete equilibrium, that is total equilibrium. I hope you got this point. And what happens when the body is in equilibrium? It remains in the same state. So now there are two types of equilibrium. One is static equilibrium. Static means there is a body, it is in rest, and there are two equal and opposite forces or two equal and opposite moments. What will happen? If it is in rest, it will remain in rest. This is dynamic equilibrium. This is static equilibrium. And what will happen if it is already in motion? And then we apply two equal and opposite forces. What will happen? This force will cancel out this force and the motion will remain. So this is called as dynamic equilibrium. Easy? Static, if the body is in rest, it will remain in rest, and no rotational effect, no translational effect. But if the body is in motion, it will remain in motion as earlier. If it was in rotational motion, it will remain in rotational motion. If it is in linear motion, it will remain in linear motion. So these are the two types of equilibrium. One is the static, one is the dynamic. So in this complete video, in this complete lecture, what we have studied is the couple, the moment of couple and the equilibrium. Give me the comments of which part was easy for you, and to solve the numericals, to get the shortcuts, the tricks of this chapter for the numericals, download the app and subscribe the channel. You will get the next videos in the app itself, and there you can get other videos also, other topics also. Okay, so see you soon in lecture number 3. Till that time, study well, take care of yourself. Bye.